Hey, we're going to walk right into the Lynk presentation by Dr. Joe Bravman because I know we're getting late in the day. And we're going to push the slam time highlights to tomorrow morning because, again, Mr. Bill Jew is now getting his award again for the second time today for the Copernicus Award. Before I introduce Dr. Joe Bravman from Lynk, I got to tell you, if we can bring up his slide deck, I think we as a service, we as a military are not really, I would say, we need to do a lot more thought process about what's going to occur when all of a sudden these capabilities arrive. And again, we have internet connected, or Internet of Things. We have capabilities in our palm of our hands that are actually connected across the globe via space. I don't think we're planning for that, and I'm concerned that we're not going to do as good a job rolling that out, cohesively across the force. But with that being said, that's just my perspective. I don't know if the gentleman in the back could bring up the Lynk presentation, but I've been very fortunate to be introduced to Dr. Joe Bravman as the chief engineer from Lynk Global for the last couple of years now. He's a wealth of knowledge with a tremendous wealth of experience in this domain. So I'm going to go ahead and turn over to brief to him. So Dr. Joe, thanks, over to you.
Thank you very much. And thank you all for coming here to listen. So Bill, Jew, and Captain Gibbons and that whole team have been really special to us. What I'm going to talk about here today is somewhat of an outgrowth of that. Originally, we were part of this same activity that you've seen with AST and with SpaceX, and that's certainly our core business today. We've been at it for 6 or 7 years now, have commercial satellites in orbit. Our approaches are a little different than what you heard from the other providers. We think that's a good thing. We think it means that the government can benefit from having a portfolio of technologies. So it's not going to be a one-size-fits-all. We're approaching it with more satellites, more proliferation, multiple satellites overhead, and not just 2 or 3, but 10, a dozen or more. But that's not what I'm here to talk to you about today. What I'm here to talk to you about today at Bill's request was looking at some of these niche capabilities that we've had the flexibility within our designs and our architecture to implement very rapidly that address related issues that the government has that are in some cases similar to commercial, but in other cases completely different. And what I'm talking about here is PNT, which is something we focused on for several years, mainly because initially the PN part of it was an outgrowth of our patented technology for how to work with unmodified cellular devices. Those devices were designed, it's a bad engineer who designs something that is more than he needs, because that's going to be money and time and a whole bunch of other things like that. So the original 3GPP standards, and for many, many years into the future, are based on a terrestrial ecosystem. There is no point in being able to talk to a tower that's 500 kilometers away because the curvature of the Earth makes that impossible, so why put it in? There's no reason to talk to a tower that's moving at 17,000 miles an hour, because how on earth is that going to happen? So what we figured out was how to do that. Now, where that is intrinsic to what we do in PNT, we calculate on each and every device that tries to register, tries to communicate with our satellite, and every time it sends a message or transacts, it's a very chatty system, it is telling us delay and Doppler. And when we co-plot those, we know where that device is. And that's kind of the underpinning of the PN part of the equation. But the other piece that people often gloss over, and I'm not talking about GPS, because GPS from the onset was a XYZ and time capability for dissemination. But most people who talk about PNT today talk about just the P and N part of it. So I'm not going to talk about that today, but I think as people who know me know, buy me a beer, I'll answer all your questions till you're sorry you asked. And I offer that up to anybody here, okay? And I've got a plethora of stories. I actually am probably the only person in this conference who actually wrote 3 out of the 4 proposals for the attitude control system on the original GPS. And had the great honor at JNC last year to spend some time with Brad Parkinson, who at 90 years old is a true immortal. But anyway, what I want to talk about today is time transfer. How you can move time that is precision and traceable to USNO or NIST or any other standard you want. How you can do that with a very small number of satellites, and how we were able to prove that in just a few months by reprogramming a software-defined satellite of ours. First chart, please, or next chart. And by the way, you'll see Dr. Norm Adams listed here. Norm is the APL point of contact. Bill introduced us to APL and also had a role in introducing all of that to ONR. And out of that formed a very tight partnership to make this stuff happen. Norm, unfortunately, was called away today and couldn't come, but I'm told in a text I got from him just a short time ago, he's actually listening to this. So if I say something wrong, Norm can't stop me, but I'll hear from him later. Next chart. Sorry? Oh, it's me. Well, I'm not sure okay. So I'm going to skip ahead a little bit. When do you want me to finish up? Okay. All right, because I don't want to stand in the way of the rest of your evening. It could go that long. Okay, so what we were funded to do was to take one of our satellites, reprogram it in such a way that we were frequency agnostic, so we could operate at frequencies where this work had been done before, and also have a time deterministic path through the satellite. And that doesn't mean it can't change, but it just can't jump around all over the place. Because what you do with twist or two-way satellite time transfer is you're constantly sending time back and forth between the source of accurate time and the receiver of accurate time. So that can change, as it obviously does at LEO, and that's one of the things we had to prove. This had been done for many years on GEOs. I'll just show you a shot of that. This is old technology. You have a geostationary satellite. You've got 2 ground stations, if you will, largely used for metrology purposes like that. Each of them contains a modem and a atomic clock. One's the source, one's the receiver, and they're constantly going back and forth with a cadence, each updating each other's time. And therefore, if the path changes, it doesn't matter. All those things cancel out. If the path is moving too fast, it doesn't matter. So this is a great opportunity for LEO. So why is LEO good if we do that? And this, by the way, these are some pictures of what I just showed you on that diagram, which is actually performed by APL. And you can see the kind of equipment they needed. They needed Gator inflatable dishes. They needed uninflatable dishes, things they could move around in vans. Whereas by transforming this to LEO, we not only pick up tens of dB of link loss. But if we pick the right frequencies, we can do this with small omni antennas, with antennas the size of cell phones, with devices the size of cell phones, with chip-scale atomic clocks. And so what I'm going to show you here is a little bit of performance data of how we did that and how APL developed the software and the technology that made it all possible. Okay, so again, made the point here, at GEO or in other ways, it's just not practical. Now we're down to the kind of size, weight, power, and cost that are part of what makes direct-to-device cellular so exciting. These, by the way, are some of our satellites. That's a stack of two. That stack, of course, can continue. The picture on the right was a transporter launch mission from SpaceX. A little bit of our space layer and our architecture. I guess the takeaway from this chart that I haven't covered already is that because of the architecture we developed as a process satellite, as a digital satellite, with the exception of certain broad limitations of antennas and things of that sort, we can pretty much do whatever we want with it. And in this case, in transitioning from this so-called through, where we're reprogramming the current payload, we can add a time reservoir, a modem, and a chip-scale atomic clock, and distribute time globally without needing to be in simultaneous contact with the ground. And in order to do that easily, we've developed for this and other missions an interface control document that touches RF, software, power, and that enables us to put something else on board the spacecraft and make it work. And that's the next phase of what we're talking about here, to actually go ahead and do that. Why that's interesting and important is that many of these things that you've heard about today and we'll hear about in the future work by putting up an awful lot of satellites and an awful lot of cost. Here, once we put that time reservoir on the satellite, we can, in theory, maintain traceable time anywhere in the world to within a nanosecond. And we've proved that. And I'll show you that in a couple of charts. And the more satellites you put up, it pretty much linearly improves that accuracy. Because most of that accuracy is the drift of the satellite atomic clock that has been drifting since it was updated an orbit ago. But if you could contact it 10 times a day, 50 times a day, you'd now be down in the 50 nanosecond range, 10 nanosecond range, worst case being off, versus with one satellite, maybe you're half a microsecond, which is still extraordinarily useful for a lot of applications. And of course, what's also interesting is that time is relevant to cell towers, as we know terrestrially. Position, location is all tied in with communications, so that having a communications platform that has these additional features is a pretty exciting opportunity and leads to other applications. So this is a little picture of what I just described as kind of an initial phase where you could take time, that little dome way over on the right, that's the time source, somewhere on Earth. We're going to drop that off in a theater supporting tactical edge, and then it can use the same technology to deliver that locally if it needs to. You can transform that image into an aircraft carrier. You can transform it into whatever CONOP you're looking at. And our dialogue with all of you is going to help us get this right. So we've got a capability here we're going to talk about, but in order to integrate this into a fieldable system is something that we've got a lot of ideas about, but I think that's where an important dialogue should take place. So this is a little bit of how the project has progressed. First, the so-called twist to LEO, and then through LEO. So 2 is, again, where we're bouncing it through the satellite, achieving that accuracy. Through is the time reservoir in space. And again, here's a little bit about a thank you really to Bill, to ONR, and of course to APL for working with us and us with them to put all these pieces together. Down at the bottom there, you see the very first thing we did, we took a flat sat of our satellite and a satellite emulator, and we did it in the lab, proved it would work. Then we loaded it up on the spacecraft a few months later. These were spacecraft that had been launched a year before, and we did it in space. This is a little shot of the hardware at APL. In order to keep a couple of things we wanted to do, we wanted to have good controls over what we actually were doing. So we wanted to make sure that even with small omni antennas, we might be getting a lot of interference. We might be getting a lot of things that, from a proof of concept standpoint, would be something else we'd have to kind of calculate out or process out. So what we had here were 2 cross-polarized Yagis tracking the satellite. We had some laboratory test equipment that essentially took the function that would be existing on the 2 ends of the time transfer, and we ran this during different passes, and I'll show you the data in a minute. This is the path of the satellite. These are typical formats that we produce for any test, any mission that we do. You can see there the trajectory of the satellite and those little things that look like arrows or vectors down to that spot on the ground. Happens to be the APL campus in Laurel, Maryland. Those represent the beam pointing right at that site, which we control during the orbit. What I think is particularly interesting here is on the right, the waveform that they use is direct sequence spread spectrum waveform. It's one they developed. It's one that's very stealthy. Obviously also survives a lot of interference issues. We didn't really plan for a particular interference environment, but what we did do was we ended up experiencing it anyway, because spectrum is spectrum. People do what they do. And when you transpond a bunch of stuff, you transpond a bunch of stuff. What we found was that we had SNR issues that were 20 dB worse than we had expected for the experiment, and it didn't care. It still held that time, and I'll show you that in maybe the next chart. So what this means is that in the real world, with jammers, with problems, this looks to have a lot of resiliency in getting that job done, and it looks like we've got a case where we're operating even 35 dB below the noise floor and still achieving lock. These are some of the tracking results we achieved. All this data was produced and validated by APL. As with any time transfer experiment, we're running it in both directions, so we're taking time from here and sending it there. We're taking time from back. So you see, in many cases here, they gave their 2 units names. They called one Lucky and one Rover. I think we were both lucky, but anyway. They plotted both of those, and you can see it takes about 10 seconds to lock. And then even with those noise bursts, it maintains lock, and it's on the order of a nanosecond. Over here, you see the same thing again. And of course, in many cases, as you know, when you're improving on a capability, you find things that you see, like the cycle slip. You say, okay, I know how to fix that. So there's been significant code updates that have enabled this thing to lock on more quickly and stay locked. But even with the very first test that was ever done, you can see we're on the order of between 0.48 and 1.41 nanoseconds difference to absolute time. So, in conclusion, it works. And not only is it possible, but it actually works well. Now we're taking it to maintain a time reservoir in space, traceable to a U.S. trusted source, and being able to drop that anywhere on Earth because of the nature of LEO orbits. I think the other thing that's interesting here is that if you know correct time and somebody's messing with your GPS or somebody's messing with something else, you've got something really good to compare it to. So this is, again, a little cartoon of the pick it up from the ground station, store it on the spacecraft, drop the time off somewhere else, and come back as often as you need to maintain the accuracy you want. And of course, chip-scale atomic clocks keep getting better, so the accuracy that's possible, even with more infrequent updates, is pretty darn good. The plot on the right shows holdover. It basically shows that if you update it on the far left, and then you have drift in that clock over the course of many hours, drift some number of nanoseconds, and you just fix that by making the updates more frequent or getting a more stable clock. So we're very excited about this next phase and taking it to where we are flying the modem and then take that into a time as a service. The last chart I've got here is to talk a little bit about this idea of a commercialization path. So clearly, I think there's still a little more work to be done. That's part of the interest of ONR and others like them. The elements to make this a very powerful capability, and I don't see anybody else really trying to deliver time like this, or frankly, time as a product, is that the basic infrastructure has to be inexpensive. The good news is that by building a platform capable of proliferation into the thousands of satellites, Lynk has come up with a very affordable platform to put this on, and it doesn't need necessarily to be on all of them, but it could be. So that's important. Synergy with the communications mission not only provides a cost benefit, but it also provides an operational benefit. That's a whole nother topic too. Okay, and finally, while we are planning to put up thousands of satellites over time, it doesn't really need that. This is a capability that with the right funding could be operational in a year. Sort of an IOC level capability. So what are the obstacles? Well, one of the obstacles obviously is competing with something that's free. And that's more important to the government than it is to commercial. Commercial is living in a dream world. They don't know what's going to happen when people start messing with their GPS. Banks don't really take it seriously. The cell tower companies don't really take it seriously. They'll talk about it. They'll say it's important, but they're not doing anything about it. When you guys mess up, people die. So I think that is an issue that we really do need to work together. And I think once we do that, I think this is a very affordable, very powerful capability for time, but also for things that need time. And with that, I'll open it up to questions. And if you have a question you don't want to ask me now, you can buy me a beer and I'll answer the question then. It'll take longer. But please, anything come to mind. Well, that's a terrible question because obviously we're the only ones in the world that could ever do this. No one else could possibly do this. But frankly, yes, it's, you know, certainly this is something that can proliferate and proliferate beyond us. And what, you know, if I for a moment forget I'm working for a company and I think about being in your shoes, you want a portfolio. You don't want one size fits all. You don't want just SpaceX or just ASP or just Lynk or just anybody. So I think there's a piece of that. Obviously, we want this to be a cornerstone of building our company, but yeah.
Well, I'll tell you that, you know, from my years as a program manager, we always viewed having time as a key capability for winning the fight. And I know we've been investing and focused on the ability we call it no gaps and no GAPA for non-GPS aided surface ship navigation, what have you, in time. So this plays right into what we need to, again, have that resiliency and that diversity of connectivity that comes to being able to operate in a GPS denied environment. So I appreciate the work you're doing on this. This is the first time that I have seen a proven out, you know, two-way satellite time transfer experiment, you know, brief. So thank you very much for doing that. And I didn't mean to insinuate that it should be given to other companies, but I appreciate your honesty with that as well.
Well, thank you very much. But you know, you make a great point, and it's a point of frustration sometimes. I have gone to various government workshops dealing with all PNT. I've gone to conferences, JNC, other conferences. I'm not trying to make anybody feel good or feel bad. And invariably, everybody talks about alt PNT, but they really mean alt PN. You know, and there is very little work at JNC, for example. You know, there was a huge pie piece, you know, maybe 90% that was GPS-centric or GPS-like. There were a few things that were really kind of crazy. There was a guy that was actually trying to transfer time to 1 femtosecond accuracy, which sounds pretty nuts. And for those of you who don't know what a femtosecond is, he started out, he says, 1 second, a femtosecond is to 1 second, as 1 second is to 32 million years. So a femtosecond is really little. But anyway, yeah, so I think time is so important. Time is important for waveforms. It's important for so many things that happen, you know. And I don't want to sound like a time geek because, I mean, this really wasn't a big part of my life. But I think this is really, really important work. It needs to be done, and it needs to be proliferated beyond us.
You know, as a program manager, I had a resource sponsor, and he'd come out of USNO, and he'd like invented this really amazing clock, and he was like a time guy. And the last thing I did was ever challenge him on time because he was so smart. And he was just the guy that's like, we got to get after this two-way satellite time transfer. So I know there's a focus on that at the highest levels of the Navy because we have those guys with that kind of skill set looking at this. So I appreciate you briefing this.
Thank you. Any other questions? If not, I have one story I want to tell when we're done. But I'd rather take a question. All right, but you got to buy me a beer later. So if you've ever, oh,
I have
go
a quick
ahead,
question.
please.
Which modems did you use for the loop, effectively loopback test at APL? And what fraction of your budget was the noise floor of the modems?
Okay, So the best person to answer that question is virtually listening to this, and that's Norm Adams. So what I'd like to do, let me come back, let me get your card, and let me connect you with Norm, and he will tell you everything you want to know about that. But right now, let's have a side conversation about it. That's a big question, and I'd like him here for that. You know, I'm smart enough to know that that's his turf, you know, and I can be a good dilettante, but you're asking a better question than that. So here's the story. And so this is not a joke. This is real. Okay, you're going to think when I'm done, this is a joke, but it's not. How many of you have ever been to the Greenwich Time Museum in Greenwich, England? I don't know how much time you spent there or how long ago you saw it. When I was there, and I was there twice, I saw this exhibit. I don't know if it's still part of the standing exhibit. Of course, that whole capability was done for the British Navy because they needed to have good time. Of course, not in nanoseconds. They were happy with a lot less, but some beautiful, beautiful pieces of equipment. It turns out for a period of time, I guess over 200 years ago, maybe going on 300 years ago, they had come across something called sympathy powder. You've seen it? No. Anyway, sympathy powder was something that somebody concocted based on some ancient Greek something or other. And what you did was you took a stick, and you rubbed it in the sympathy powder, and then you took a dog. You struck the dog with the stick. You put the dog on a ship, kept the stick back at headquarters. And when you wanted to have a time demarcation, you took the stick and you struck the ground and the dog would yelp on the ship. And it somehow passed field trials. And then they tried to take it into operational capability. And guess what? It didn't work. And they spent decades trying to figure out if they lost the recipe. But that's a real thing. And I don't know if the exhibit's still there, but when I was there, it was wonderful. I don't know if any of you have seen it.
Well, thanks, Joe. Thanks, Dr. Bravo. Let's clap it up. Let's give him a round of applause for hanging in here late for us. Tomorrow, we're going to start at 0800. We're going to do some assured and alternate PNT conversations and follow it with a panel. So look forward to everybody starting at 0800 tomorrow here in this space. Thanks so much.
Thank you very much.